Hello everyone, good evening. So we are in the session 13 of ray optics. Today we'll look at the idea of aberrations that we have when we are making the image formation due to a lens, and then we'll begin with the optical instruments. So today we'll talk about the microscope. Okay, so we'll first complete the leftover part of the refraction through lens. In this, right, we talked about the lens equation. So there is one more what we can say variation of the lens equation, that is what we call as the Newton's formula. Okay, so Newton's formula is the equation that relates the position of the object and the image with respect to the focal points. Like if you take a lens, like we can think of a convex lens here. Okay, so you see here let us consider this as the object. Okay, the distance of the object from the focal point, this is focal point 1. So focal point 1 we are calling it as x1. Here this side let us say we have the image. The distance of the image from the focal point 2 is x2. The Newton's formula for the x1 and x2 values, right, is the x1 into x2 value will be equal to f square. It's a very simple formula. So instead of looking at the distance of the object and the image from the optical center, generally we will measure the distances from the optical center, right? Instead of measuring from the optical center, we are measuring from the focal points. Now we can see how this value f square is equal to x1 into x2 will come. So if you use the lens equation, right, from there we will be able to get this. So here what we have is the distance of the object from the optical center. We will refer to it as what u, right? So u will be equal to what? We are measuring it to the left side. So it will be minus of f plus x1. What is v value? V will be equal to what? This is f x2. So v will be f plus x2. Now we will go for the lens equation. What is the lens equation? 1 by v minus 1 by u is equal to 1 by f. That is the lens equation, right? 1 by v minus 1 by u is equal to 1 by f. So we'll just have to substitute them. What we'll have? 1 by f plus x2 minus of 1 by minus of f plus x1. This is equal to 1 by f. So minus minus will become plus. We can take an LCM. What we'll be having? F plus x2 into f plus x1. That will be in the denominator. Numerator, f plus x1 plus f plus x2. This is equal to 1 by f. Now what we will have to do is we will have to cross multiply. We will have to cross multiply and then simplify it. So maybe you can try to work it out parallel with me. So what we need to be doing here, we will have to cross multiply and then write the expressions. So check it, what we will be getting. If you cross multiply, right, so what we'll have on the left side, this is f plus f, 2f plus x1 plus x2 into f. Right hand side, what we'll have? F plus x2 into f plus x1. So this is what? 2f square plus fx1 plus fx2. Right side will have f square plus fx1 plus fx2 plus x1 x2. So fx1 is cancelled, fx2 is cancelled, 1 f square also we can cancel. So left side we have 2f square, right side we have f square, right? So left side will be having f square, right side what will be the remaining part? X1 into x2. So the Newton's formula is nothing but we can look at it like what? Variation of the length equation. So normally we have the length equation relating the V value and U value. There V and U are measured with respect to what? The optical center. Here the x1 and x2 values are measured with respect to what? The focal points. Okay. So though we have given the example of the convex lens here, because you see the derivation, right, we have done for the general, so it can be for any lens. Okay, so this is what we'll refer to as the Newton's formula. I mean, it's not like, we'll get questions on this Newton's formula, but sometimes, right, they might just give some question where they will mention the distances measured from the focal points, distance of the object measured from the focal point 1, distance of the image measured from focal point 2. So there they might not mention that use the Newton's formula, but what is the thing that we need to be, getting there? It is the Newton's formula. Whenever we see the distances measured with respect to the focal points, right, the first thing that should come to our mind is the Newton's formula. What is it? F square will be equal to what? X1 into x2. Focal length square will be equal to what? X1 into x2. Okay, so this is what is the Newton's formula that relates the focal length to the distances measured from the principal focus, f1 and f2. Okay, then the aberrations concept, right? So when you are having the image formed into a lens, we'll have two types of aberrations that can happen. One is what we call as the chromatic aberration. Other one will be generally referred to as the spherical aberration. Okay, so aberrations means what? The image will not be formed properly. The image will not be formed properly because of some reason. So we'll see what is the reason for that. The chromatic aberration, right, from the very name itself it will be evident. What is it? We are referring to as the colored image formation. So what is this chromatic aberration? Means colored image formation. So what actually happens is, when you look at a lens, right, remember the biconvex lens, focal length, when we have done the derivation, we have seen that the focal length depends upon what? It depends upon the refractive index. Focal length formula, right? I hope you guys are able to recall the formula. Focal length will depend upon the refractive index of the lens. But what we have already studied, remember from the Cauchy's formula, the refractive index of the lens material, right, will depend upon the particular color of the radiation. Why? Because the mu value will depend upon the lambda, right? We have seen in fact that mu will be having inverse relation with lambda, means for the red color light, lambda will be more, so mu will be less. For the violet, lambda will be least, so mu will be highest. As a result of which, what happens is the corresponding focal length. So when you say focal length of the lens, with respect to violet, it will be having a different value for focal length. With respect to red, it will have a different focal length. Because of this, what happens when you are passing, say for example, the object is releasing white colored light, which is a mixture of all the colors. Like in this case, you can see, right, when you are passing a parallel beam of white rays, what do we observe practically? The violet will be focusing onto one point. This will correspond to the focal length of the violet. Red will correspond to another point. That will be relating to what? The focal length of the red, because focal length will depend upon the refractive index, right? Refractive index will change from lambda value to lambda value, which means if you have a white object, right, the image of the white object will not only appear colored. Why it appears colored? Because the different colors are getting split. It will also look blurred because it is spread, right? The image will not be at a particular point, it will be blurred. Why? What is the reason for that? The reason is mu value of the lens, right, will be different for different colors. This will come from the Cauchy's formula. Because mu is different, the corresponding focal length is different, means what? The kind of convergence that will happen will be different for different colored lights. So this kind of defect, where we see that the different colors are actually getting split, what do we call it as? We will call it as chromatic aberration. We will refer to it as what? Chromatic aberration. Now, how do we remove this chromatic aberration? Already in the case of the prism, we talked about it. If we make a combination of two prisms, where one prism will cancel the one prism is say for example causing the dispersion. If the other is able to converge them, then what we'll have, we'll say that combination of the prisms is achromatic, isn't it? Because one is dispersing, other is actually converging them, and we have seen what is the formula there also. So in case of prism, what is the condition that we need to require to have the no dispersion case? Because the dispersion is there means we'll see colors, so we should have no dispersion. So here we'll have to, just like the way we have made a combination of prisms there, here what we need to do, we have to make a combination of lenses. So we have to choose the combination of lenses in such a way that we will be giving an achromatic effect, means whatever the dispersion that is caused by one of them, right, the other should actually cancel it. So in place of using one single lens, because if you use one single lens, what happens, we will definitely get the chromatic aberration. So to remove it, right, what we do, we basically use a combination of 2 or more lenses, so that we will be able to achieve this achromatic combination. So this is generally called as what, achromatism. So we have to suitably choose the lenses so that if one is dispersing means other should be able to converge it. So what do we call this combination of lenses as? Achromatic combination. This is just like the way we choose the prisms. Okay, so this is what we'll generally call as the chromatic aberration, where the image will be formed, it will be colored and also it will be blurred. The other type of aberration that we'll have in case of lenses is what we will be referring as the spherical aberration. The spherical aberration is because, see, when we talked about the image formation due to a lens, right, remember we said we are going to use the assumption of paraxial rays. Paraxial rays means what? The rays that will be almost parallel to the principal axis and that will be very close to the optical center. So the paraxial rays will be what? Almost close to the principal axis, very close to the optical center. But if you have, like, large object where the rays are coming and touching the tip of the lens, we will refer to them as the marginal rays, the rays that will come to the tip. So generally, because of the curvature effect, right, what will happen is the converging or diverging of the marginal rays will end up being different from the converging or the diverging of the paraxial rays. So generally, we said one of the assumption that we keep using is what? The paraxial rays. But practically, if you have a lens, right, it is not like the rays are only going to come very close to the principal axis, right? You will get the rays coming to the tip of the lens also. So when you look at the behavior of the marginal rays, they would be converging or diverging to a different extent than the paraxial rays. So as a result, what we will have is, you can see if you have taken the parallel beam of rays, the paraxial rays are converging to point F, means the marginal rays are converging to a different point F dash. Means what? If you are taking a point object, then that point object, ideally what we expect it to give a point image, right? Point object should give a point image. Extended object will give an extended image. But what we see here is, for the point object also, we can see the rays coming from the tip of the lens, they will converge to different point. The rays coming close to that optical center, they will converge to different point, which means we would not be able to get a point image. So the inability of a lens to form a point image, even for a point object, right, is generally what we refer as the spherical aberration. It comes because of the, the marginal rays at the tip of the lens, the curvature effect, right, will come into picture. As a result, they will be getting converged or diverged to a different extent than the paraxial rays. And as a result of it, again, even for a point object, right, we will not be able to get a point image, we will get a extended image. Okay, so this is what we will call as the spherical aberration. Okay, and how do we remove this spherical aberration? Instead of using a biconvex or a biconcave lens, we can use a lens which is having curvature only on one side. So the lenses that will have curvature only on one side is what? Like we can think of a plano convex lens. The lens is having curvature on one side. That is one usual approach. Otherwise, we can even take combination of lenses which are separated by a distance which will be related to the respective focal lengths. So if we're taking, a combination of two lenses, means we should separate them with a distance which is equal to what? F minus f dash. So here we don't need to really get into the details of how we will be able to exactly remove the spherical aberration, etc., because in our purview, right, we just need to understand the concept of both these aberrations. That is it. Okay, so exactly how we are going to remove them, we can get a broad idea. That is sufficient. Okay, so we don't need to mathematically prove as to how, if you take lenses separated by the d is equal to f minus f dash value, how this will be able to remove the spherical aberration. Those details, the mathematical details, will not be required much for us. Okay, so this is about the two types of aberrations we have. What are the two aberrations? One is the chromatic aberration, that will come because of what? The mu value of the lens being different for different colors, and the image will be what? Blurred and colored. We will remove it by using what? Combination of lenses, which we will call as what? Achromatic combination. The other type of aberration is spherical aberration, which will come because of the curvature at the periphery, or the marginal rays effect is also what it is sometimes called. It is also sometimes called as what? The marginal rays effect. Okay, so this will remove either by choosing lenses which will have curvature only on one side, or we can also remove it by making a combination of lenses with some suitable adjustment. Okay, so what is the adjustment we are talking about here? If we separate them by a distance which is equal to what? The difference in the focal lengths of the lenses, right? Then we will be able to remove this spherical aberration. Okay, so these are the aberrations that we have for the image formation due to the lenses. So with this, right, we have covered the discussion about the refraction through lens, and whatever the things that we have discussed, right, is something that we are going to use in our study about the optical instruments, because optical instruments, right, are going to be formed from these devices. Like, we are going to use, mostly we'll use lenses, and we can even use mirrors also. So optical instruments that we are going to talk about are one is the microscope, and the other is the telescope. Okay, so we have a fundamental difference between these two. Microscope general purpose is, you have a tiny object. Micro means what? It refers to tiny object. So you have a tiny object, you want to see an enlarged view of that. What is the main purpose of the microscope? You should be able to see a magnified view of the object, so that, like microorganisms, bacteria, if you are somebody who is into biology, you will be able to understand a lot of these microorganisms, right? You will be able to study them only when you see through this microscope. So in your bio laboratory and all, you generally have these microscopes. But here we will be able to understand how exactly that optical instrument will work. And telescope purpose is, if you are having a celestial body, whether it is a planet in the solar system, or a distant star, etc., when we want to understand or study the surface of that particular planet, or the periphery of that star, then we will be able to use this telescope. Okay, so we'll see how exactly the telescope is basically for what? For viewing objects which are at very long distance. Microscope is if you have tiny objects, then to get a magnified view of the tiny object. That is the purpose of the microscope. Okay, so before we get into the microscope discussion, right, we need to understand, not just for the microscope, even for the telescope also, right, this visual angle concept will be important. So what is this visual angle? See, when we talk about view of an object, right, it is not about the real size of the object. So whatever is the real size, like you see here, there is a real size of the object. This object will actually form an image on the retina. where this object will form an image, it will form an image on the retina. Now you see here there is an angle. There is an angle that is the angle subtended by the image. Because of properties of straight lines, right? The angle this side also will be same. So when we talk about the view of the object, right, what we are referring to is this angle formed. So same flower, right? When you take it farther from you, what do you observe? You will see that if you go farther, means what is it that we are going to observe? We will observe that the object will be subtending a smaller angle. So this angle that is subtended by image of any object on the retina, right, is what we call as the visual angle. So whenever we want to understand the view of any object by our eye, the view is measured by using the visual angle. It is not about the actual size of the object. The actual size of the object may be anything, but when we say view of that object, right, the view is represented by the visual angle. So when the visual angle is more, it means what? We will be able to see, because the image on the retina will be large. That is what matters, right? So visual angle need to be high. The visual angle value needs to be high. Okay. So if you look at generally how do we get the visual angle, right? Let us say we are having this object which is at a distance UO. What is the distance of the object here? UO, and height of the object is H. So you can see from this right angle triangle kind of a thing, right? What is the tan theta value here? It is what? H by UO. What is tan theta? It is what? H by UO. And since the angles that we are talking about here are what? They are going to be small angles. Because when you see through our eye, right, you will not only be able to see that object, you will see the entire surrounding of it, which means the theta that we are referring to, we will consider it to be a small angle, because our visibility, right, will cover lot of area. So whatever the angle that is subtended by a particular object, right, we will consider the angle to be small angle. Under that assumption, right, if theta is small, then what we can say, tan theta will be approximately equal to theta. But we should keep in mind this theta must be in what? Radians. The theta must be in what? Radians. So the angle subtended here, theta will be equal to what? H by UO. What is UO? The distance where we are actually keeping the object. Now we will get an idea how we can maximize this visual angle. See, H we cannot change, right? Can we change the value of H? H we cannot change. Then what is it that we can do? We can keep on. What we can do? We can keep on bringing the object closer and closer, because if you bring closer means what happens? The denominator value is going to decrease, right? The denominator value is going to decrease, which means what? Theta will be increasing. So remember, what is the relation we have? Theta is equal to what? H by UO, right? You decrease UO means theta will be increasing. So we'll get a feeling that we can increase the visual angle of that object when we bring the object closer and closer to our eye. But here in our 12th syllabus, we don't have the study of eye and eye defects, but you'll study in your 10th standard that we cannot bring the object as much close as we want. There is a distance from the eye. If you bring the object lesser than the distance, means if you bring an object closer than this distance, right, the eye will not be able to see the object clearly. So this distance is generally what we call as the near point, and this distance is indicated by capital D. How are we indicating this near point? Capital D. Okay, so whenever we want to achieve higher visual angle, the general understanding is what? We should bring the object closer and closer. But what is the limitation for that? We cannot bring it closer than our near point. Generally for a healthy human, right, the near point will be what? Some 25 centimeters. Generally for a healthy human eye, the near point will be 25 centimeters. Means we cannot bring it closer than the 25 centimeters. So here we will not take the value, we will generally refer to it as what, D. We cannot bring it closer than D, okay, which means the maximum visual angle that an object can automatically create, because if you have an object means when I want to create the maximum visual angle for that object, where I am going to keep the object, I'll keep the object at the near point. That corresponding value of the visual angle, right, we'll call it as what, theta naught. Theta naught will be equal to what, h by d, because we are going to keep the object at the near point. Where we are going to keep the object, we'll keep the object at the near point, okay. So this is what is the maximum visual angle we can create with our naked eye. Here remember, we are not using any optical instrument or anything. We are just giving this maximum visual angle by adjusting the position of the object. So where we have to keep it, we have to keep it at the near point, then we will get the maximum visual angle, okay. Now whenever you say you are using an optical instrument, right, whenever we say we are using an optical instrument, what is the purpose? It should be giving a larger view. That's what we are saying, right? Larger view means we are talking in terms of the visual angle. So the optical instrument should do something, some phenomena, so that it will be able to create a visual angle which is more than theta naught. That's the whole purpose, right? The optical instrument should be, if we say that no, optical instrument should be giving us a magnified view of that object, means what? Optical instrument should do something, some phenomena, so that it will then be able to give us a higher value for the visual angle. Okay, so this theta naught is what? This is the maximum visual angle we can achieve just because of our naked eye. We are just positioning the object, because if you have any microorganism or anything, right, you can keep it at our near point and then you will be able to see it, right? So that's what you are calling as the maximum visual angle with a naked eye. Optical instrument we are using means that should give us a visual angle which is more than this. Okay, now whenever we talk about this optical instrument, like microscope, here we're talking about, say, we'll begin our discussion with the simple microscope, then we'll go to the compound microscope also. But for any of these, right, we will define this term called as what? Magnifying power. So whenever you look at a microscope, they will mention the magnifying power. If you happen to go to the laboratory and see it, right, they will mention like 10x, 20x, 4x, like that they will mention. Okay, so magnifying power, basically what is this? 10x means 10 times, 20x means what? 20 times. Okay, magnifying power is basically the factor by which image on the retina can be enlarged by using the microscope. Here we're talking about the magnifying power of the microscope. Okay, we'll see what is the difference between a simple microscope and compound microscope. We'll see it later, but here for any of them, right, we will use this magnifying power. What is the magnifying power? It is nothing but the visual angle formed by the final image. Because of the microscope we are getting the final image, right? The visual angle formed by the final image divided by the visual angle formed by the object when we are keeping at the distance d. This is what? This is our theta naught. So if you say that visual angle formed by the final image is theta, you have to see when we go to the discussion about the specific instrument, we will be able to know how we will get the theta value like that. But already we know theta naught. What is theta naught? It is h by d. H is the height of our original object. Theta naught value is what? H by d. What is this? The visual angle formed by the object when we are simply keeping it at the distance of the near point. Okay, so this is what we will refer to as the magnifying power. Obviously, when we are using a microscope means this is the point of interest, right? So we want to have a higher magnifying power. So any microscope we are having means we want to achieve a higher magnifying power. Okay, so this simple microscope, right, before we go to the simple microscope, we'll just look at this theta naught value. What is this theta naught? This is the visual angle that is formed by keeping the object at the near point. Okay, so what is this? As we already seen in this right angle triangle, right? Tan theta naught is equal to what? H by d. Since we consider the angle to be small, tan theta can be approximately to theta. So this is what is our theta naught. Okay, so we'll have to remember this because we are going to use this. So in all the calculations henceforth, right, we are going to be using whenever, whether it is a simple microscope or a compound microscope, right, whenever we want to finally go for this magnification or the magnifying power, M formula, right, capital M formula, we will use this theta naught. What is theta naught? H by d. H is the height of the original object, divided by d is what? The distance of the near point, which will be what? 25 centimeters. We don't need to tell the value, so maybe we can just keep it in the back of our mind so that if required, right, we'll use it. Now we'll come to the simple microscope. Simple microscope is a very simple entity. It's just a converging lens of short focal length. We will see why do we need to have a short focal length. We will see. First, let us look at what is basically a simple microscope. What is simple microscope? It's nothing but a converging lens of short focal length. That's it. Now we have to understand how this converging lens will be able to provide us the magnification. See here, we are keeping the object. We're keeping the object between the optical center and the focal point. Remember, for a convex lens, right, if you are keeping the object between the optical center and the focus, what is it that we are able to? So this is not pole, you call it as what? Optical center. So if you keep the object between the optical center and the focus, remember, for the convex lens, right, the image formed will be what? It will be a virtual image. What will be the image formed? It will be a virtual image, correct? So here you can see the image formed is what? It will be a virtual image. Now the angle formed by the image in the eye, this is theta here. Again, what is tan theta? It will be h by uo. What is tan theta value? H by uo. Okay, since theta is going to be a small, that is the assumption we are doing with, theta will be equal to what? H by uo. Okay, so what is it that we have? The theta value will be equal to what? So this is the visual angle here. This is the visual angle. Okay, so this is the image. So theta will be equal to what? H by uo. And the magnifying power, because that is what we are interested, right? What is the magnifying power? Theta, the visual angle that is formed here, divided by theta naught. What is theta here? H by uo divided by h by d. Theta naught is what? H by d. You can see h is cancelled. So what we'll have? The magnifying power m. So what is the magnifying power value? So all these formulae we just have to, because on this microscope and telescope, right, the questions we are going to get, we'll get straight on the final formulae, because very rarely we'll get questions on modifications. So what is the magnifying power here? We are getting m is equal to what? D by uo. What is the magnifying power? It will be what? D by uo. Okay, now this is the magnifying power for the simple microscope. This is the magnifying power for the simple microscope. Okay, now the thing is, simple microscope, right, we will use it in two arrangements. So in the heading itself, you are seeing, what is this that you're seeing? Relaxed view or normal adjustment. What do you mean by the relaxed view or the normal adjustment? The relaxed view or normal adjustment means the final image will be formed very far, so that our eye can actually see it without getting strained. So when you will be able to see anything which is without straining our eyes, because the closer it comes, we'll have to strain our eyes to see. When we can see anything without straining our eyes, when the image is formed at very, very far distance, what is it? That's what we call as infinity, right? So when the final image is formed at infinity, that particular arrangement is what we'll be referring to as the relaxed view or the normal adjustment. And for that to happen, right, for that to happen, your UO should be equal to what? F. Because when you will get the final image at infinity, when you are keeping the object almost at the focus, when you're keeping the object almost at the focus, right, that is when we will get the final image at infinity, which means what? The UO value should be equal to what? F. Now, in that case, right, the magnification that we'll get is basically what we call as the magnification of the simple microscope in normal adjustment or relaxed view. What do we call it as? The magnification of the simple microscope in normal adjustment or relaxed view. So what is it? We may just represent this by m infinity. The infinity represents what? The final image is formed in infinity. That will be equal to what? D divided by, for this to happen, what is the UO value must be equal to F, right? So D divided by F, that's it. So this is what the magnifying power when we have the relaxed view or the normal adjustment. It's a very simple thing, right? So we'll just have to remember the formula. Now I'll tell you why. In the beginning I said what? We should have lens having a short focal length. Now you will be able to understand, right? Because when the focal length is less means magnifying power will be more. When the focal length is less means the magnifying power will be what? More. That is the reason why we will require a lens which is having a small focal length. Okay, but it's not like, you know, we can keep on decreasing the focal length, because there will be other effects that will come into picture. Remember, you know, the aberrations. We keep on decreasing the focal length, right, we'll start getting what? Aberrations. Generally for a simple microscope, right, if you are getting the magnifying power somewhere around 3 to 4, that's a good magnification, because if you go beyond that means you'll start getting the aberrations. Okay, so this is what the magnifying power of the simple microscope, in which arrangement? The normal adjustment or the relaxed view. In this we are forming the final the final image at the infinity. Okay, now we will go to the second way of arranging this. The second way of arranging it is the final image is formed at the near point. The final image is formed at the near point. Near point means what? The distance will be d. Okay, so here again we are keeping the object between the, what we say, the optical center of the lens and the focus. We are getting a virtual image. Okay, so here the object distance is u0 and the image is formed at the near point. This is the near point. Okay, now already we have got these results. What are the results? Theta will be equal to h by uo, and magnification is what? D by uo. All these things we already have. Now what we need to do is, if we are forming the final image at the near point, for that we have to find out what is the magnification factor value. See here, the object distance is what? UO, but we are measuring to the left side. So object distance, we'll take it as minus UO. What is the image distance? D from the lens, but this is also measured to the left side. Minus D. What is the lens equation? 1 by V minus 1 by is equal to 1 by F. Means what? 1 by minus D minus UO. Minus minus is cancelled. What we'll get? This 1 by minus D will take it to the right side. Left hand side will have 1 by UO is equal to 1 by D plus 1 by F. What is 1 by UO? 1 by D plus 1 by F. Now straight away we will use it. Look at this magnification factor formula. M is equal to what? D by UO, means it is like what? D into 1 by UO, right? So D into, what is 1 by UO? 1 by D plus 1 by F. Multiply it inside. So in this case the magnifying power, we will call it as what? M subscript D. So previously we used this infinity. So here why are you putting D? Because This is the case where the final image is formed at the near point. So sometimes we will also refer to this as the constrained view. What we'll also refer to this as constrained view. Why we will refer to as constrained view? Because when the image is formed at the near point, we will have to strain our eyes. We'll have to strain our eyes to see the final image. Okay. But what is the benefit in that? Well, obviously, when we are able to see relaxed view when the image is formed in infinity, why should we strain our eyes? Because you see the formula, right? What is m infinity d by f? What is the magnifying power in this case? 1 plus d by f means in this case we are going to get a higher magnifying power. In this case we are going to get what? A higher magnifying power. But at what cost? At the cost of straining our eyes. We'll have to strain our eyes, then we will be able to get a higher magnifying power. Okay. But in this case, right, as we said, the thing is, with a simple microscope, we may not be able to go and achieve very high magnifying powers because of the limitations. You will start getting some aberrations. Okay. So generally, if you want to get a higher magnifying power, like I said, 10x, 20x, right, you will have to design what we call as a compound microscope. Compound microscope will use combination of lenses so that the aberrations can be removed. Compound microscope is basically what? It's a combination of lenses where we will be able to remove the aberrations. Okay. So we'll see what is this compound microscope. But this is about the simple microscope. Simple microscope can be used in two arrangements. One is the relaxed view or the normal adjustment where the final image is formed in infinity. What is the magnifying power formula? D by f. Okay. And in case of the final image formed at the near point, which we call as the strained view, what is it? The magnifying power will be higher. What is it? 1 plus d by f. But you will have to strain our eyes to see the final image here. That is the only thing. Okay. So this is about the simple microscope. Now we will get into the compound microscope. As I said, compound microscope will have combination of two lenses. One we will call as the objective. Second one is the eyepiece. So compound will have two lenses. One is called as what? Objective. Second will be what? Eyepiece. Okay. So here the objective and eyepiece, right, will have some specifications. The objective as well as the eyepiece will have some specifications. We will see what is specification in terms of whether, because in the previous case, right, remember in case of simple microscope, what we said, the lens should have a smaller focal length. Why? Because we have seen once we get the magnifying power formula, what we are able to see, if the focal length is less means magnifying power will be high. So here the objective is basically the one that will keep closer to the object. So this is where our object is. This h is what? Height of the object, right? The lens that we're keeping close to the object is called as what? Objective. The lens that we keep close to the eye is called as what? Eyepiece. Here also the objective and the eyepiece will have some specifications. We will be able to understand about the specifications once we see the working, because then it makes sense why we are choosing some specifications. Okay. So first we'll go through the working of the compound microscope, then we'll talk about the specifications and the reason for the specifications. Okay. So here look at this situation. We are keeping the object at a distance UO from the objective. Okay. And objective focal length we are taking it as what? FO. And its image is formed at VO. The image formed by the objective, is going to act as the object for the eyepiece. The image formed by the objective is going to act as the image for the eyepiece. So here you can see that distance from that eyepiece, we are calling it as what? UE. So the gap between these two lenses, right, is what we call as the length of the microscope. So what is this? This is basically what? VO plus UE. What is the length of the microscope? It is nothing but what? The separation between the objective and the eyepiece. What is it numerically equal to? VO plus UE. When I add both of them, we will get what? The separation between the objective and the eyepiece. So these, as I said, in the optical instruments, we will get questions mostly based upon the straight formula, whether it is the JE mains level or the NEET level. Okay, so rarely we will get questions in JE advanced on the optical instruments. JE advanced, you will get questions on combinations of lenses, etc. But particularly on the formula, we have, very rarely got questions on this. But the mains level or the NEET level, right, you will get questions straight based on the formula. We don't need to even go beyond that. The only thing is we have to be clear in terms of how the formulae are coming. So length of the microscope is what? VO plus UE. Why VO plus UE? You can see here, whatever is the image formed by the objective, that is the object for the eyepiece. That's it. So the length will be what? VO plus UE. This is what we call as the length of the microscope. Now, if you look at the way we will set up the microscope, that is also important. The way we are setting up the microscope. Look at the way we are setting up the microscope. How are we setting the microscope? We are setting up the microscope, compound microscope, in such a way that the object, the original object, is placed beyond the first focus of the objective. Because if you keep it beyond the first focus, right, then definitely what we know, the image of this will be formed on the right side. It will be not only formed on the right side, it will be what? It will be an inverted and real image. The image formed here, right, this is we can call it as what? I1. The image formed after the first lens, that is the objective lens. That will be what? It will be a real inverted. And also we can see it will be what? Magnified. Also it will be what? Magnified. So if you are keeping the original object beyond the first focus, then what we will get? The image formed because of the objective will be what? It will be magnified image, real and inverted. Okay, so the understanding is the H dash, right, will be more than H. H dash value will be more than H. Okay, now let us come here. The eyepiece, right, will have to form an virtual image. Then only the eye can finally see it. Eyepiece has to form a virtual image. Means here this image, right, I1 is going to act as an object for the eyepiece. I1 is now going to act as an object for the eyepiece. So where I1 should be positioned, the adjustment of the lens should be in such a way that this image, right, will be between the first focus and the optical center. This image I1 is now going to act as the object for the eyepiece, right? This should be between what? Between the first focus and the optical center, so that this is now going to form a virtual image. The final image is what? It will be a virtual image. Okay. Now this is what we will call as the setup of the compound microscope. So what is setup of the compound microscope? The first lens, which is the objective lens, the one which we keep close to the object, that should be giving you a real inverted and enlarged image. When it can happen? When we keep the object beyond the first focus. And this image is now going to act as the object for the eyepiece. This should be between the first focus and the optical center of the eyepiece, so that the image formed by the eyepiece will be what? It will be a virtual image. It will be a virtual image. Okay. So here when we look at the working of the compound microscope, obvious things will be, we will be interested to know what is the length of the microscope. Already we have seen what is the length of the microscope. What is the length of the microscope? It is what? VO plus UE. That is the length of the microscope. The other thing that we are interested in is what? The magnifying power. What is the other thing that we will be interested in? We will be interested in what is the magnifying power, right? So look at how we will calculate the magnifying power. So here this is the theta, right? This is theta. What is this theta value? Theta value, because we are going with the assumption theta is a small angle. You see here, this is what UE, right? So theta will be equal to what? H dash by UE. Theta is equal to H dash by UE. And what is our theta naught? The visual angle formed by any object with our naked eye. What is theta naught? It will be what? H divided by D. Remember, that is the theta naught. So what is the magnifying power here? It will be theta divided by theta naught, right? Which is what? H dash by UE divided by H by D. So D will go to the numerator and E will come to the denominator. So look at this. It is what? H dash by H into D by UE. What is the magnifying power M value? H dash by H into D by UE. Now the thing is, H dash is what? Height of the image formed by the objective. H is what? Height of the object. Remember, what is it that we have for a lens, right? The H dash by H. This is what we call as the linear magnification. What is this? Linear magnification will be what? It will be the what is the linear magnification for a lens? It will be what? V by U. Image distance by object distance. But image distance we are measuring to the right side. So it will be what? VO. Object distance from the, this is the lens, right? From the lens we are measuring to the left side. Image distance is right side, object is left side. So we have to take it as what? Minus UO. We have to take it as what? Minus UO. So H dash by H value, right? This is equal to what? Minus VO by UO. What is H dash by H value? It is what? Minus VO by UO. Okay. So we'll just have to substitute it. This is coming from where? The linear magnification formula for the objective. It's coming from the linear magnification for the objective. So look at this. What is it? Minus VO by UO into D by UE. Minus VO by UO into D by UE. So here if you just look at the magnifying power value, I'll talk about the negative significance. Negative significance means what? Negative indicates what? It indicates that the final thing is what? Inverted. Negative indicates what? The final visual angle is measured in the opposite orientation. Okay. But if we just look at the magnitude, right? What is the magnitude of this? If we take the modulus, right? Just take the modulus value. What is the magnitude of this? It will be what? VO by UO into D by UE. It will be what? VO by UO into D by UE. Now, why this minus comes, you know? Because look at this. The final image is what? Inverted. Here we have the object as what? Erect. The final image is what? Inverted. That is the reason why we are getting the magnifying power as negative. The negative value indicates what? The final image is inverted. The compound microscope, right? The final image formed will be what? Overall it will be what? Inverted. This is another point that we need to keep in mind. So what is the magnifying power formula? VO by UO into D by UE. VO by UO into D by UE. Okay, so this is what is the general magnifying power for any compound microscope. But here also again we'll talk about those two things. What are those two things? Relaxed view. What is relaxed view? When the final image is formed at the infinity. So here, you know, we look at the general formula. What are the two general formulae? The general formula for the magnifying power and general formula for the length of the microscope. What is the length of the microscope? VO plus UE. That is the length of the microscope. Okay. Now what we'll do is we'll go and look at the two arrangements. What are the two arrangements? One is we want to get the final image at infinity, that is the relaxed view. Second is the final image is formed at the near point. These are the things, right? First is what? The final image is formed at the infinity. Second is the final image is formed at the near point. Okay. So here we'll just start with these two standard results. This is the magnifying power VO by UO into D by UE. What is the length of the microscope? VO plus UE, right? Now we are going to look at the relaxed view. Relaxed view means what? The final image is formed at very, very long distance, infinity. If it is formed at infinity means simply look at it. This I1, right, should be exactly at focal length of the eyepiece. That is when you will get the image at infinity, right? Means simply our UE value should be equal to FE, that's it. UE value should be equal to what? FE. That's it. So what will be the magnifying power? VO by UO into, in place of UE, what will substitute? FE. This length should be equal to what? FE, that's it. What about the length of the microscope? VO plus, in place of UE, what we substitute? FE. So if we are having the compound microscope used in the relaxed view, if you are having the compound microscope used in the relaxed view, right, what is the thing that we have? The magnification factor or magnifying power, right? In place of UE we will get FE, that's it. Because the final image has to be formed at infinity means the image I1 is coming just after the objective. I1 should be exactly at the focal point of the eyepiece, that's it. That's when you will get the final image at infinity. Accordingly the formulas will change. Okay, this is what is the relaxed view. Sometimes if you are feeling that there are a lot of formulae like that, right, what I would suggest you do is you remember the general formulae. I mean, it's not like you have so many formulae here. You will have totally, I think 6 or 7 formulas, that's it. So maybe you can remember all of them, but if not, right, you will try to remember the general formula and then you should be able to derive the required case in the examination, which I would not really advise. Why? Because it can be some time killer, and even if you make a mistake here and there, right, you could be losing that question. Okay, so this is about the idea of the relaxed view. Now what we'll do is we'll go to the constrained view. What is the constrained view concept? When the final image is formed at the near point. So final image is formed at distance D. D is what? The near point distance, which we are saying is what? 25 centimeters. Again, we'll begin with the same general formula. What is general formula? Magnifying power is equal to what? VO by UO into D by UE. So you have to keep one thing in mind. This is the magnifying power modulus value. Actually will come as negative. Why it will come as negative? Because it will be inverted. Because of a compound microscope, the final image will be what? Inverted. And what is the length of the microscope? It is what? VO plus UE. That is the length of the microscope. So here we are looking at the final image is formed at the near point. For this, right, look at the eyepiece. Okay, object distance U, we are measuring it to the left side, minus UE. Image distance V, that is also measured to the left side, minus D. What is the lens equation? 1 by V minus 1 by U is equal to 1 by F. Means 1 by minus D minus of 1 by minus UE is equal to 1 by FE. This is what eyepiece focal length. Okay, now here we can see minus into minus becomes plus. Again what we'll have is, I'll write down here, what we'll have, 1 by UE is equal to what? 1 by D plus 1 by FE. 1 by UE is equal, just we are using the lens equation. What we are doing there, we are using the lens equation. Okay, now once we use the lens equation, right, what is it that we are getting? We are getting 1 by UE is equal to what? 1 by D plus 1 by FE. Now we will have to do the simplification based on this. Look at this. The magnifying power, right, M is equal to what? VO by UO, that is not changing, into D by 1 by UE, right? What is 1 by UE? 1 by D plus 1 by FE. Multiply, what is it? VO by UO 1 plus d by fe. This is what is magnifying power. This is what is magnifying power. Okay. And what about the length of the microscope? Length is what? VO plus UV rate. So from here, look at this. 1 by UV is equal to what? D plus FE by D into FE. Means UV will be what? D into FE by D plus FE. UV is what? D into FE by D plus FE. That's it. So we got the values. So we got what is the magnifying power, and we are also getting what is the, so what is the magnifying power here? You can see it is what? VO by UO into 1 plus D by FE. That is the magnifying power. What is the length of the microscope here? VO plus, in place of UE, what we will write? D into FE by D plus FE. That's it. These are the two values in case of what? In case of the compound microscope, where we are arranging it such that the final image is formed at the near point. Okay, so we'll have to just make a note of both these formulae. So here I am again and again telling you that the formulae, final formula, are important. So the magnifying power, we are putting it as M subscript D, because the final image is formed at the near point. What is it? VO by UO into 1 plus D by FE. What is the length of the microscope here? VO into D into FE by D plus FE. Okay, so just make a note of these results. In the next class, what we'll do is we'll continue our discussion about the specifications of the eyepiece and the objective lens. So specifications and how the specifications will be justified based on the purpose of the microscope, and we'll solve problems. We'll solve problems based on these formulae only. Okay, so just make sure that you go through the formulae once, and as I said, right, mostly questions are going to come on the basis of the formula itself, and then we will start getting into the telescope. Again, there also we are going to do some derivations, and questions will mostly come from the final formula itself.